Hey everyone, my name is Nishant. I'm a software engineer on the Docker core team, and today I'm going to talk about the Docker approach to orchestrating Linux containers while tolerating failures. Let's start with, what is a Linux container? We are at container camp, so I probably don't need to talk about this much, but we all know that containers have been around for a while. But really, the introduction of the Docker project in 2013 really brought them to the public and made them really easy to use. And we've all seen the container revolution since then. Just to give you sort of some numbers, the image pulls on Docker Hub have been growing significantly fast, and we just recently reached 5 billion pulls, which is a pretty cool number. But containers are not the entire story. Real-world applications need a lot more to run. Docker has brought about a new perspective. People are talking about microservices, deploying applications at scale. But this brings up some interesting problems. We heard some of these from the talks before. What infrastructure are you going to choose? How are you going to deploy your applications? What about security, networking? How do you scale? How do you tolerate failures, and so on? We need fundamentally new tools and abstractions, and container orchestration is the solution. I was just looking at this graph on Google Trends, just seeing sort of the interest in Docker over time versus sort of orchestration-related terms, technologies, and so on. And you can see that while Docker has grown significantly, orchestration is just now beginning to grow in popularity, and people are beginning to consider containerized deployments. But orchestration is hard. It's a distributed systems problem. As Michael also described in his talk just before me, there are lots of issues that distributed systems could have that you need to consider, and some of which being, machines can go down, your network is not reliable, your packets can drop, latency can cause issues, and so on. So at Docker, really, the question we asked was, can we make it easier to deploy real-world applications, containerized applications, in a way that Docker, the original project, made it easy to deploy containers? And the answer to that question is essentially swarm mode in Docker 1.12. So Docker 1.12 is the latest release, which, as some of you might know, came out with inbuilt orchestration, which we call swarm mode. So the goals essentially were to make it really simple to set up and use a distributed cluster. And the fundamental idea is that it should be seamless to move from a small-scale development or test environment to a production environment. The behavior of your application, as defined by Docker, should be identical to what you expect on your machine or on a small cluster and in production. And starting with 1.12, Docker has inbuilt orchestration, and the easiest way to orchestrate Docker containers is now Docker itself. Multiple Docker engines can be simply connected to form a swarm cluster really quickly, and it's then really easy to manage your applications on that cluster. So this is a brief outline of my talk. This is how I'm going to proceed. We're going to start talking about the swarm topology first. How do you create a cluster? How do you add nodes? How do you remove them? What do nodes mean? And so on. Then we're going to dive deeper into cluster state. How does Swarm manage cluster state for fault tolerance? And then finally, we're going to talk about application state. How do your applications run in the way that you expect them to? And I do have a demo on the side that I hope to keep up with as the talk progresses. So let's see how well that goes. So let's start with the Swarm topology. We have a Docker engine, and we have one command here. And really, the simplest way to set up a cluster with Swarm is to run this one command. You say Docker Swarm init, you specify an address that this engine is reachable on, and that's it. You have a one-node cluster running, and what you can do is add more engines to this cluster. So you do Docker swarm join, specify the address of an existing engine in the cluster, and you have a 2-node cluster. It's that easy. You can run this a few more times, and you have a 5-node cluster. Now, if you're wondering what these reds and greens mean, essentially there's 2 kinds of nodes that a swarm cluster can have: worker nodes and manager nodes. Worker nodes simply run tasks. In the case of Docker, tasks are containers. They simply run tasks that they're told to. Managers, on the other hand, have additional functions. They can not only run tasks, but they also interact with the user through the API and accept requests. And they also maintain distributed state and reconcile any differences from what is expected. It is really easy to promote promote workers to managers, and then or demote managers to workers. So what we've done with this is made it really simple to manage your topology in a really transparent way. I would like to demonstrate this right now, but before I do that, I want to point out that one of the decisions we made with this was to have a cluster that is secure by default with end-to-end encryption. How many of you have in the past struggled with TLS or just ended up deciding not to use it because it was so complicated? I've definitely faced a lot of issues myself and seen a lot of GitHub issues come up from time to time. But with the new swarm mode, what happens is that each manager has a certificate authority, and nodes that get added on are cryptographically verified. And so there are other features like certificate rotation, and you can integrate your own CA, and all communication in the cluster is encrypted. So you don't need to bother with setting up TLS at all. It's done for you. And with that, I would like to actually show what that workflow looks like. All right, so what I have is a few droplets running on DigitalOcean. I'm just going to use one of them to set up a swarm cluster. So we have 3 nodes called Manager 1, Manager 2, Manager 3, and then 3 nodes called Agent 1, Agent 2, Agent 3. So I'm going to say Docker swarm init. So this is the address of this manager, and when it looks like I forgot to clean up from my testing. Okay. All right. So that's it. We have a new swarm cluster set up. You can see that it has given this command to me, which includes not only a join address, but a token. And this token is basically what is used to ensure that any new node that joins the cluster is verified. So all we're going to do is simply run this on every node. Node join the cluster, node join the cluster, and then node join the cluster, and then last one. Okay, so we have a 6-node cluster, and we can confirm that by saying docker node ls. And as you can see, we have 6 nodes, one of which is the manager, indicated by the leader status, which we will get to briefly. But I want to also promote these other manager nodes. So I'm going to say docker node promote manager 2 and 3. And then finally, this is what my cluster looks like. I have 3 managers and 3 workers in my cluster. And that's how easy it is to set up. I can demote the managers if I want. I can promote more workers or add nodes just as easily. So the next part of the talk is about managing cluster state. How do these managers and workers together actually accomplish what they're expected to? It's a brief digression about the Raft algorithm. Is everyone here familiar with or vaguely familiar with the Raft algorithm? All right, so Raft is a popular distributed consensus algorithm. Essentially, whenever you have a distributed system, a bunch of distributed machines, you want a way to have consistency in the state. And to summarize it really briefly, Raft ensures that there is a single leader in the cluster that performs all updates, and it has ways to elect a new leader if the current leader goes down, and it performs log replication, essentially making sure that all the leader logs are replicated to the other nodes. But what you basically need to know is that consensus is maintained as long as a majority of nodes are up. So Raft ensures that as long as half or more than half your nodes are up, your cluster is fine. And this is what the Raft consensus layer in Docker Swarm looks like. So this is built on top of the HCD Raft library. What we've done is we've implemented an in-memory distributed state store. So what this is that this is highly optimized. It has indexes. It has batched operations. It has several optimizing features on top of the underlying Raft algorithm, which makes it really fast to perform cluster updates and other cluster operations. It's strongly consistent. It holds desired state. That is, what is the structure of the cluster? What services are running? What applications are running? What are other properties that need to be saved? And it is secure. The Raft log is encrypted. So, as you can see, the Swarm managers are crucial. Going back, only the managers form the Raft consensus group. So what's essentially happening is that the managers store state, and if managers go down, then Raft ensures that that all the cluster details that are actually important to salvage the cluster are actually saved. So managers are important. One of the nice features is that now you don't need to set up an external KV store like you had to with Docker Swarm in the past, or perhaps with other orchestration systems. As long as the majority of the managers are running, you're fine. And this also makes sure that there's no single point of failure. You can submit requests to any manager, and they're all routed to the leader. The second layer of communication that we have is worker-to-worker gossip. So gossip is a different algorithm for communication. It's eventually consistent, which means that all information will be spread eventually and everyone will have it. It's kind of like a lot of people gossiping in a room and spreading information. This mostly spreads networking related information because it's not urgent for all nodes to have it. The advantage of this is that this is a high volume peer-to-peer algorithm, and it really reduces the load on the Raft layer, because we don't want to store everything in the Raft consensus, making it slower. And as mentioned before, all communication here is encrypted too. And then when you put it all together, this is what a Swarm cluster looks like internally. So we have the Raft consensus group, we have the gossip network, and then managers talk to workers using gRPC, which is an RPC library. All right. So now getting to the third part of the talk, and this is really the more interesting part because everyone wants to run applications in the end. That's why we're doing this. So with Docker Swarm now, we have a higher level of abstraction. You're all familiar with Docker Run, but now Docker supports services using Docker Service Create. So what a service is essentially a declarative specification. It's a way to specify what exactly you want to run and what it should look like. And the job of the cluster is to make sure that it's running in that way. It should be scaled up. It should be scalable up or down, and you should be able to run it seamlessly on a cluster, no matter what the size. The simple way to run a service is through the Docker service create command. So it's as simple as you say Docker service create. You can specify how many replicas you need. In this case, 3. Specify a name for it, a network that it should be on. You can publish a port for it, and then you finally specify the image. Before we move any further, I want to just kind of go slightly deeper into what this publish is here. With Swarm, we have this idea of a routing mesh that makes it really easy and simple to configure networking for your cluster. So essentially, what's happening here is that when you say publish 8080:80, the port 8080 is reserved for your service, and all nodes in your cluster now expose that port for that service. So the idea is that you can hit any node that you want, and you'll be routed to a container of this service. The other cool thing is that every service gets a virtual IP. There's an internal distributed DNS server which helps with service discovery, and there's an internal internal load balancer that round robins requests to between containers of your service. So this is something that we're really looking forward to seeing used in different ways, because this has significantly reduced the issues that we were facing with orchestration in the past with our experience with users and customers. I'd like to go back to the demo now and set up a service. So because we don't have too much time, I'm going to use an image that I already built before. It's a simple website served using Nginx. So I'm going to say Docker service create. Let's give it a name. Let's say we want 3 replicas of it, and then we publish port 8080, and the image is going to be front-end image. This is on my account. That's it. So now you can see the running services with service ls. We see that the front-end service is running with all 3 replicas. We can see the individual tasks that it's running by using service ps. So we have this. As you can see, we have 3 tasks running as expected, and 2 of them are running on the manager nodes. 1 of them is running on the agent nodes. We can go and verify that they're actually running by hitting one of these endpoints on the browser. Great. So that's all the service does. It says hello. What happens if a node fails? Let's say the node on the right fails, and it's actually running 2 containers. The cluster detects that something changed. The desired state of 3 replicas is not the same as what you're running right now, and it's going to take the appropriate action so that it converges back to what you want. You can easily scale your service by just specifying how much you want the new scale to be. And there are several more features like global services, configurable rolling updates, node constraints, or constraints based on node labels, different kinds of restart policies, scheduling that's resource aware, plugin aware, and a lot more that's coming in the next couple of releases. And again, going slightly deeper into sort of how this actually works. So we have managers and workers, and the block on the top is what a manager internally looks like. It has 5 parts. It has an API that the user actually interacts with that takes in your command and sanitizes it and makes sure that it's reasonable. And then It submits it to the orchestrator, which looks at what the command is asking for, and depending on how many tasks it needs or how many containers it needs, it creates those. And then the allocator actually assigns IP addresses to these containers. The scheduler then assigns nodes to these containers, essentially where should they run. And then finally, the dispatcher dispatches these tasks out to the workers. In addition to dispatching tasks, the dispatcher also maintains a sort of heartbeat connection with the workers to make sure that it knows that the worker is there, and that in case a worker goes down, then it can stop dispatching tasks to it. On the worker side, we have a worker part that connects to the dispatcher and checks on any assignments that it might have got, and then an executor which just simply executes what's given to it. And it also reports the state of the tasks back. And so considering both of these, when nodes fail, if a manager fails, then it is Raft that takes care of ensuring that your state is not lost. And if a worker fails, then what happens is that the dispatcher detects that a node went down. And then if it was running any containers that were relevant to a running service, then the orchestrator picks that up. The orchestrator figures out that, oh, these containers went down, I need to create 2 more. And that's the same thing that happens on updating or scaling a service. And then the allocator, scheduler, dispatcher kick in with their usual roles, and then the cluster is restored back to the expected state. And just to briefly demonstrate how that works, so we have this service running on these 3 nodes, manager 1, manager 3, and agent 3, as you can see in this column. So what we're going to do is we're going to bring down agent 3 and see that the service is, the task that's running on agent 3 is rescheduled. So I have an alias to kill agents. Okay. And so it's going to take a short while before changes are detected and propagated. So right now, the dispatcher still hasn't found out that the agent went down. On the next heartbeat, it will. And while it does that, we go further and note that if everything fails, that is, if all your managers go down or if consensus is lost, then there is still an option to recover something by using what we call force new cluster. This is similar to an option that etcd also provides. Essentially, Raft stores snapshots periodically. This is configurable in Swarm, but based on the last snapshot that a certain manager had, you can actually use that to restore a new cluster and then build starting from there. And we'll check on the service in a bit, but to conclude, if you haven't kept up with some of the details that I described, really the key takeaway points from this talk are that with Docker 112 Swarm mode, it's really easy to create and maintain a cluster that's failure resistant and has really simple defaults for networking and security, which are handled out of the box. And finally, Docker can now run services which are declarative specifications of how you want your application to run. Obviously, in my example, I've just run one service, but a real-world application would have multiple services talking to each other and discovering each other on the network. There's a lot more coming in the next couple of releases. Contributions are always welcome. All of Docker open source is on GitHub. Most of this orchestration stuff is in a repo called swarmkit, which is separate from Docker, but kind of integrates into Docker now. And I would also like to thank some of my coworkers who helped prepare this talk. Nathan, Alex, Aaron, Drew, Jana, and Dong. This is my first conference talk, so I needed some help there. And that's it. Thank you. And before I finish, I'm just gonna go and check on that service. So you can see that this last line, this task was killed and it was shut down, and a new one was created on manager 2. So that's it. We don't have much time, but if you're interested in seeing Force New Cluster or other features, please come talk to me after.